Welcome back, ladies and gentlemen. We are going to be studying organic chemistry, which is a bit of a change compared to the stuff we've looked at so far. Up until now, we've been really looking at the nuts and bolts of chemistry, understanding the fundamentals of how all these pieces work. But now we're going to take a bit of a step back, and we're going to do kind of what we did in grade 10, right? In grade 10, we learned a bit of the language of chemistry, and we learned about covalent and ionic, and we learned about the naming rules for each of those, and then we learned how to turn those naming rules into sentences and then into paragraphs through stoichiometry. Well, we're going to start off by teaching you guys another alphabet, another fundamental naming rule system for organic molecules. But the question arises, what in the world is organic? Well, in the early 19th century, a Swedish chemist called Jones Jacob Berzelius, maybe? I'm not Swedish. Classified compounds into two categories. Another binary compound, another binary choice. We've seen that before. There he is. Those obtained from organisms, which he called organic, so, from you or I or a dog or a flea or a plant, and those obtained from minerals, called inorganic. In this case, is the Greek prefix meaning not, or different from, I should say. So what are we seeing? Inorganic coming from the ground and organic coming from living things. Seems a pretty simple system. Problem was when this chap rolled around. He was a Friedrich Wöhler, and he produced an organic compound, specifically urea, from two inorganic compounds. So urea, for those who don't know, is part of P. And the original assumption was that you could only get urea from P, from organisms that are alive, that produce the organic compound. But then Wöhler came around and demonstrated, no, actually I can take two rocks, put them together, and I can get something. This was a huge change because up until this point we kind of assumed that there must be something unique about living organisms in terms of how chemistry works. Like, there are certain things we dig out of the ground and there are certain things that we get out of living things. But then we discovered that wasn't the case. Now, on the one hand, that makes certain things seem a little less special. Oh, you mean urea can be made from anything rather than having to extract it from P? But it also meant stuff like, oh, you mean I don't have to kill whales and extract part of their bodies in order to make oils? I can dig them out of the ground? Well, that's very convenient. Saves a lot of whales. So these days we break things down into organic compounds and inorganic compounds still, although for a slightly different reason. These days we do it mostly because the things we classify as organic are really important in certain ways, but very different from other things. So we keep this binary system not necessarily because it's the best, but because it's an arbitrary division between left and right, up and down that we can use to understand things. It's a tool, that's all. So organic compounds are compounds containing carbon. Organic chemistry is basically the study of carbon in detail. However, not everything that has carbon is organic. Organic things have carbon, but not everything that has carbon is organic. Wonderful, Mr. C. Could we clarify? Carbon monoxide, carbon dioxide, carbonates, bicarbonates, carbides, cyanides are considered to be inorganic. Okay, what do all these have in common? Can we break it down? Yes. For our purposes, we will say that any compound that contains carbon and hydrogen is organic. But really, a lot of this is just tradition, right? People were coming up with these categories and using them long before Wöhler came along and managed to figure out that actually I could make P from two rocks. Sorry. So carbon and hydrogen. Okay, so think about it, right? Carbon dioxide, there's no hydrogen in there, right? It's just CO2. Carbon monoxide, no hydrogen. So you need both carbon and hydrogen for it to count as organic, at least for our purposes. Organic compounds are covalent compounds and can include other nonmetals as well. We're often going to see carbon and hydrogen, of course, is required, but we're also going to see oxygen and nitrogen. Those two are pretty big. And because they're so major, they come up a fair amount. This does result in some rather quirky things, like organic sodium chloride. Has neither carbon nor hydrogen, so Sure. Admittedly, this is because of a difference in the term organic. In your everyday shopping, organic doesn't mean what it does in chemistry. I mean, it kind of did originally, but then marketing got a hold of it and they ran with it. Organic these days usually just means without treatment in a factory that you know of. Organic in chemistry, though, means it's got carbon and hydrogen, okay? Okay, so that's our fundamental definition. What else are we going to look at? There are millions of possible organic compounds, literally uncountable, because carbon bonds incredibly easily to itself. Remember, carbon's in the middle of the periodic table, right, of the ionic table, so it can either gain or lose. Great at sharing. It's got a nice electronegativity, pretty balanced, nothing too fancy about it, so it all works out very well. Carbon is very flexible. It can also bond very easily to hydrogen, nitrogen, oxygen, sulfur. These are very common compounds in organic chemistry. You have these elements inside you right now. Carbon compounds can form chains or rings. So we can have structures that go out this way. We can have structures that come around to make a circle. There's a lot of different options. Because the thing about a chain or circle is I can always make the chain or circle just a little bit bigger. Carbon can form double or triple bonds. You've seen me draw some of these occasionally in class, occasionally even in the videos. We're going to talk about them in more detail now, and we're going to see what they actually mean. So, yeah, here we go. Chemical Co-Incorporated, the organic division and the inorganic division. I myself spent most of my time studying inorganic chemistry rather than organic chemistry, but, you know, they're both incredibly useful. So, a little bit of practice here. In your book, you guys will see this. I've got a list of different chemicals, which ones are organic, which ones are inorganic. So remember, we're looking for carbon and hydrogen. So I will pause dramatically. Hopefully you pause the video and give these a try. See if you can figure it out. Okay, probably long enough for you to pause. Now, here we go. I'm going to show you the answers. There they are. So inorganic ones do not have hydrogen. This one doesn't have hydrogen. This one doesn't have hydrogen. This one has hydrogen, but no carbon. We need both. If we don't have carbon and hydrogen, it doesn't count. Same with down here, CO doesn't have it. The rest of these have carbon and hydrogen. Sometimes they have other things too, but they have carbon and hydrogen. That's the key. So the difference here, organic compounds, because they are covalent, melt or boil at low temperatures, because all covalent compounds do that, at least compared to ionic compounds, which we understand do not do that. With, of course, the exception of water. Water is not an organic compound, right? It doesn't have carbon in it. If your water has carbon in it, then it's probably soda pop because it's a carbonated beverage. Do not conduct an electric current. There's an exception here called acetic acid. Don't worry about it. For the most part, you do not conduct an electric current. But I hear a question asked in the back quietly because no one's actually here. If we can't conduct an electric current, how come we can electrocute ourselves with like a hairdryer in the bathtub or something? Excellent question. And the answer to that is because you sweat. I mean, there's a little more to it, but when you sweat, you put salt on your skin. Salt in water can conduct a current. You by yourself cannot. So you're mostly non-conductive, except when you decide to add a conductive element to the mix, an ion. Whoops. Inorganic compounds conduct electricity quite well. 3, many organic compounds burn in oxygen to form carbon dioxide and water. We know that. That's combustion. It's the combustion reaction which we showed you guys originally in grade 10, burning. Many inorganic compounds do not burn easily. Burning, as I mentioned, is when you add oxygen to something. Inorganic compounds tend not to burn. They tend to rust. That's sort of their version of burning. They just do it slowly, if you're lucky. Finally, the formulas tend to be way more complex on the organic side compared to the inorganic side. NaCl versus C12H22O11, which is good old sugar, sucrose, and C27H46O, which is cholesterol, fat inside of your body that stores energy. Well, sometimes. Yes, this does mean that the naming rules for organic compounds are a little bit more involved than the naming rules that we had for ionic compounds. I apologize for that. There's a reason we haven't covered them until now. On the plus side, even though the rules are a little more complicated, they're always the same pieces: carbon, hydrogen, nitrogen, oxygen. So there's only so many bricks in the Lego kit. Putting them together is just a matter of knowing the rules. So at least we don't have a lot of different bricks, right? Normally, on the periodic table, we've got, what, 180 different possible options? We've only got to work with 4. 4 out of 180 isn't so bad, but yeah, that's looking a lot more complicated than some of the stuff we had originally. Can't win them all. So, the basics of organic compounds. All organic compounds, chemistry revolves around carbon and hydrogen bonds. Okay, we covered that. So we got to understand carbon-hydrogen bonds before we can get anywhere. So, reminder, how many valence electrons does carbon have? Would carbon and hydrogen make a covalent or an ionic bond? How many electrons can carbon share? And how many bonds does a single carbon want to make? Pause dramatically, let you try to answer. 4 is the magic number. We're going to see the number 4 come up a lot. Carbon has 4 valence electrons. It wants 4 more valence electrons in order to make that combined full valence shell. It's going to do it covalently because its electronegativity isn't high enough to go ionic. So, remember the Lewis structures? It's been a while since we had to do those. There they are. I think you can already see what's going to happen. This and this are going to share. So these two wrap together, and when they wrap together, that's one bond. Carbon needs, of course, 3 more, 4 in total. 1, 2, 3. So you're going to need 3 more hydrogens to fill it out. And that's going to basically be the rule it's going to work. Hydrogen is going to fill out the missing pieces of the carbon. And then once it's full, it's happy. How many bonds will the following atoms want to make? How many electrons can they share? All right, can we figure it out? Carbon, hydrogen, we just figured that out. I said carbon, 4. Hydrogen, 1, because it only needs 1 more electron. Remember, that first valence shell is only hold 2. Oxygen, how many electrons does it need? Why, it needs 2, doesn't it? Nitrogen, halides. Oh, which one's the halides? It's another name for the halogens. Here we go. Oxygen is 2 steps from the end, so it needs 2 more electrons. It can have 2 more bonds. Nitrogen is 3, so that means it can do 3 more bonds. Halides are 1 step away. That's your fluorine, your chlorine, your iodine, your bromine. They are 1 step away, so they only need 1 more bond or 1 more electron. Okay, what does all this mean? Right? This is all review of stuff we did before. So what happens when I put all this together? Carbon can combine covalently with many different elements thanks to its flexibility. We call these materials organic if they possess both carbon and hydrogen in covalent bonds. Another name is a hydrocarbon. I mentioned that word before. Here's where it comes from. Hydro, meaning hydrogen, carbon, meaning carbon, because as we've mentioned before, chemists are bad at naming things, so they called the thing with hydrogen and carbon the hydrogen-carbon thing, hydrocarbon. There are many categories of hydrocarbon that we will be looking at in this unit. We break hydrocarbons down into multiple different sections. Some of them are pretty boring, like, I don't know, aldehydes. Yeah, they're pretty boring. Others are very exciting. Students are always very excited. Alcohols, ooh, suddenly everyone gets very intrigued. Others are very interesting, such as aromatics, because they're what make smell. And yet, we're going to learn about all of them, at least superficially. So first things first, sources of hydrocarbons. Okay, so there are 3 basic places we can get hydrocarbons, he says as he raises 4 fingers. 3 basic ways. Option 1. Gee, I wonder where's the first place that we can get organic compounds. What was the original definition of organic compounds again? Oh, right, living things. You and all living things produce organic compounds as a result of being alive. Many, like enzymes and proteins, are incredibly complex. We are not going to go into enzymes and proteins. If you have done biochemistry or biology, you've seen enzymes and proteins. You know they're super messy because it turns out that you are a wonderful, complex, rich person with a tapestry of interesting mechanics all behind that amazing brain of yours. And, the rest of you too. So beyond living organisms, you also have fossil fuels. Oil, natural gas, coal, stuff we dig out of the ground. These are oil, coal, and the rest are made of the remains of living things, and over the millennia have been distilled into simpler forms. This is the starting point for most organic chemistry. I usually have this discussion with the students. This is one of those tricky things. If we all stopped driving gas cars tomorrow, we'd still need oil. We'd need oil because oil is used to make plastic for your cell phone case or the chair you're sitting on or the buttons on your shirt. Oil is used as the starting point for tons of different organic chemistry, and the reason for that is very simple. A, we've had a lot of it lying around, and B, it's easy to transport. It's just like a liquid start. It's a liquid, literally. It's a liquid starting material that we can then turn into anything we want. It's very easy to transport, to pipe it around. It seemed like we always had tons of it, and until fairly recently, we didn't realize that there was a downside to doing that. We were just like, whatever, it's just like stuff out of the ground. What's the big deal? Oh, the big deal is we took it out of the ground, and now we don't have anywhere else to put it. Whoops. But yeah, we've been working on organic chemistry using oil for all of these things, but that's the downside. Even if things like cars or power plants stop using fossil fuels tomorrow, we'd still need oil in order to do a lot of organic chemistry, for the most part. I mean, you may have heard of biofuels, right? Biodiesel, biofuels for cars. That's where you grow something and then turn that thing into a fuel that you can burn in your car. That's getting organic compounds from living things. The downside is that, we eat living things. So if we have to choose between growing plants to turn into plastic or growing plants to turn into meals, I'd rather eat. But plastic pays better. And that's a difficult problem. Like, everyone needs to eat, but you'd get more money for growing plants to turn into plastic. That's the kind of calculation that somebody has to make that's not going to go well. So, not a good sign. Lastly, we got synthesized. As was demonstrated by Wöhler, you can take inorganic materials and synthesize them into organic, but this is generally expensive, right? Like, living things do it for free. Fossil fuels were living things that we just dig out of the ground, also pretty easy. Doing it by synthesis, that means you have to set up a giant factory. You got to mine rocks out of the ground. You got to grind them up, turn them into something, process them. Compared to that, it's a lot easier just to distill down a plant or dig some oil out of the ground that was already distilled for you. So synthesis is an option, but it's an expensive option, right? So we're kind of stuck with this one for now, at least until one of you brilliant people come up with a way to use this or this more easily, hopefully. So on page 5 here, you guys got a little discussion that talks about turning oil from the ground into the various types of gases and gasolines and other hydrocarbons that we use. And what you're going to see there is that there's a lot of information about how big. So this column here talks about how big the carbon chain is, right? And how many carbon atoms. So 1 to 5. They boil pretty easily. They're mostly a gas. And what are they used for? So you can see over here, there's a little bit of a reading for you guys to do. It talks about it a bit in your notes. Moving on. Hydrocarbon structure. Ah, yes. The malcanes, the family of hydrocarbons that chemists would rather not talk about because they're all so mean. Oh, poor methane. The alphane, the profane, it's swearing. The butane, because it's so violent. All of these. The spentane, it's tired. Texane, it's got a gun. All of these, of course, are just going to be jokes off of the basic naming rules that we're going to use for this particular thing. All right, let's take a look. There are many different types of hydrocarbons. We already said this because you can just add another carbon. You can arrange the existing carbons in a new way. So if you remember, allotrope, that's a word that you probably recall. Allotrope, same element, different crystal structure, crystal lattice. So allotropes have different physical and chemical properties as well as different names. Diamond versus carbon versus nanotubes versus graphite, all of these things. Isomer, here's a new word, an isomer. Same molecular form, different structure. So it's the same basic idea. Here we had elements arranged in a different way. Here we have molecules arranged in a different way. So instead of it being one building block that I just change how I put it together, it's multiple building blocks that I change how I put them together. In the same way, they've got different properties. So I don't think you're super surprised to learn that if, like, for example, I detach your arm from your shoulder and attach it to the bottom of your foot, it's going to behave differently. It'll also probably be messy with blood everywhere, but, you know, hopefully we can do it properly. It'll behave differently than if I keep it in the same place. So the only difference here, as I said, is instead of us taking apart individual atoms and putting them together in a new way, we're taking larger molecules and putting them together in a new way. So instead of working with one piece at a time, we're working with 2, 3, 4, 5 pieces at a time and putting them together. The fact that these multiple pieces all come sort of pre-existing and they are used multiple times is sort of a useful quirk, but not strictly unique to organic chemistry. It just comes up a lot here, which is why it's so important to talk about. So here are two isomers of C5H12. Okay, so this is an organic compound because it's got carbon and hydrogen, right? Got the two hallmarks, carbon, hydrogen. There are 5 carbon and there are 12 hydrogens. So let's think this through, right? First option, I could put the 5 carbon in a row. 1, 2, 3, 4, 5. Okay, and then I put the 12 hydrogen just attached all around. So we see here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we'll see that each carbon is attached to 4 other things because carbon wants 4 things, right? So like this carbon on the end here has got 1, 2, 3, and then 4 that goes to this guy. Now this guy in the middle here doesn't have as many hydrogens because it's got carbons on either side, right? So that is how these structures build out. And this is what we would call a chain of hydrocarbons because it's just one after another put forward in front of itself. But I said that there are going to be isomers. There's going to be 2 different ways I could assemble this. Can you think of another way that I could take the same pieces and put them together? I'll leave you to think about it just for a few seconds. Maybe pause the video, see if you can draw something out. Give it a try. I'm going to show you the answer right away. Here it is. What? Huh? What did I do there? Let's take another look. Over here we've got 5 carbons. There's still 5, right? 1, 2, 3, 4, 5. But now the 5th one isn't on the end. It's down here. I replaced one of the hydrogens from here. I took like this guy here out, and I put one of these guys at the end in its place. So this is what we mean when I say that I take like a whole molecule at once and I move it around. I'm moving that around. I moved it from the end to over there, over here in the middle somewhere. So these are 2 different isomers, and they actually behave differently, even though they are made of the same material. There's huge differences in how they boil and how they interact, how they react, all of those things. So chemists have different ways to draw isomers because, of course, they do. They can't be consistent on anything, can they? Except for naming things badly. So 3 structural diagrams can be used to show the structure. There's 3 basic ways to draw this, okay? So the first one I just showed you, right? The first one is going to be a complete structural diagram. It's called that because it shows everything, again, with the scientists bad at naming. So there it is. There is all of the things. This is what we would call like our entry-level diagram style. This is what you do when you're first starting out because you're like, I want to make sure I understand this and I want to show everything, right? This is level 1. Then you got the condensed structural diagram where you basically merge all the hydrogens together because they're just sort of repeating over and over again. So you still see the same basic structure, right? There's still 5 carbons in a row, but now instead of drawing the hydrogens sticking out in all these different directions, I just squeeze them down into one place. But this isn't lazy enough for some chemists, so what do? The line structural diagram, because again, chemists name things exactly what they are, and it looks like that. What? Huh? What we're seeing here is that each point is a carbon. So what they did was they took this one, and then they said each carbon, okay, so there's 1 carbon here, there's 1 here, 2, 3, 4, 5. So there's still 5 carbons, but they just show them as the vertices, the points of the lines. They don't draw the hydrogens because they just go, look, 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 you, me, we're smart, we understand this. We know that the carbons always want 4 bonds, 4 connections of some form. So this guy at the end must have 3 of them, and this dude in the middle must have 2 of them because that's the only way to make this work. So basically they just look at this and go, I understand that you understand what's going on. So I'm not going to draw it because I know you're very smart and because I'm very lazy. So that's basically what happens. I'm going to use all 3 of these interchangeably. I will generally start with these because you guys are still learning, but towards the end of the unit, we're going to get a lot of this. If you want to use this, go right ahead, right away. You can do that. Jump to level 3. I don't care. You want to stick with this the whole time? Go right ahead. I don't mind. Whatever works for you. If you ever get stuck, just make sure to ask me. I'm fine with using any of them. I just tend to be a little lazy and not want to draw those hydrogens. When you've drawn as many hydrogens as I have, you don't want to draw any more. Okay, so here's a bit of an overview of all the different forms, right? We've got our molecular form. We know that one, right? This is sort of the basic chemical formula that we've used before. Our empirical form, we talked about that in another unit. You've got your condensed form, which we just saw. Over here, we've got our displayed form, or the complete form. Then we've got the structural form, which sort of is a combination of the condensed and the displayed. And then finally, the skeletal or line form, because again, laziness. Of course, we're going to see, right, there are other symbols down there. We got like some O's, there's 2 lines. I don't know what's going on with that. We'll explain that as we go. But this is the basic idea. There are a couple different ways to show this. I don't care which one you use. Choose any. So, saturated versus unsaturated. What? What are we talking about here? Okay, well, let's break it down. Un is opposite, right? So there's option 1 and there's option not 1. So it's another binary choice. So there's going to be one of them is going to be one way and the other one's going to be the opposite way, whatever it is. So once we learn what one of these is, we know what the other one is by it being at the opposite, okay? In the context of solutions, saturated means full. And for hydrocarbons, this holds true, except now we are talking about the number of bonds. I mean, we didn't do solutions yet, so saturated means full. I think you probably know that. So full of bonds. That's what we mean when we say a hydrocarbon is saturated. So it cannot have any more bonds. It has all of the bonds it can. Okay, so here are some examples. The first one there is a saturated hydrocarbon. The second one is unsaturated. What's the difference? Well, what you see is that up here, I've got more hydrogens, right? Like this guy at the end here has 3 hydrogens. Look at this guy in the end, it has 2. This guy has 2 hydrogens, this guy has 1. Where's the extra hydrogens going? Well, they're getting kicked out. That's what being unsaturated means. There's less hydrogens. Maybe I should change that to be less hydrogens instead of number of bonds. Well, whatever, it's up there for now. Maybe I'll change it. But what do we see, right? The carbon still needs the same number of bonds. It still needs 4 bonds. So what does the carbon do? This carbon has 2 hydrogens, that's 2 bonds. It's got 1 bond to the other carbon, that's 3 bonds. And then it's got 1 more bond to the other carbon, that gives it 4 bonds. This is called a double bond because it's double the bonds. Again, the scientists bad at naming things. Oh, they should have sent a poet, as the saying goes. A saturated hydrocarbon has as many single bonds as possible. An unsaturated hydrocarbon has some double or triple bonds. Double means 2, triple probably means 3. Why is this important? Well, we're going to see this when we go into the naming rules next time. The naming rules for these hydrocarbons are going to be related to how many single, double, or triple bonds there are. And they change how certain things are going to behave. We're going to see that when we go forward here, but generally speaking, you may have heard of the fact that you're supposed to avoid saturated fats. Those ones. Unsaturated fats, like, say, a vegetable oil, are supposed to be better for you. You can tell if a fat is saturated or unsaturated based on how well it turns into a solid. As we're going to see, these two have different properties. This one stacks together very well, so it turns into a solid very easily. This one doesn't. This one has a hard time getting close to each other, so what happens? Liquid. But we'll talk more about that as we go forward. And right now, since we've covered a lot of the basics here, I'm going to leave it there with hydrocarbon naming, and I will see you guys next time.